Chapter B, we're going to talk about the ideal gas. Now, first of all, we're going to use the notation at the beginning here that capital V is the volume, capital T is the temperature, and temperature we can assume is in kelvins unless we state otherwise, but the convention is to use the capital T for kelvins and then lowercase p for pressure. And for kelvins here, remember that with kelvins, 0 K. Now, when you write this out, Kelvin usually use lowercase, and then when you use the abbreviation, you use uppercase. So this is minus 273.15 degrees Celsius, which is about minus 460, almost minus 460 degrees Fahrenheit. Now let's look at the ideal gas law. We can start with Boyle's law. Historically, this goes back centuries. Boyle's law, and we hold one of these constant for these laws. So T, temperature, is considered to be constant. Then we find that the pressure is proportional to 1 over the volume, which means we can write that the pressure times the volume, and here's a reminder that the temperature is constant, the little subscript. This is equal to a constant. We would like to get a picture as to what is going on with Boyle's law. And here I have a balloon with air. And if we push on the balloon to make the volume smaller, the pressure will build up inside. So this is verified in the laboratory to have this relationship, that the pressure is proportional to 1 over the volume. Next we go to Charles's law. So Charles's law, we're going to consider for Charles's law the pressure to be equal to a constant. And if that's the case, then the volume is proportional to the temperature, which by dividing by T, we can write V over T, constant pressure, reminder there, constant pressure is equal to a constant. Now for Charles's law, if we keep the pressure constant, but heat up the gas, we find that the balloon will expand. And the pressure will then be whatever the pressure is outside the system. So we do this slowly. So the pressure can be considered constant. So the volume is proportional to the temperature. And notice that pressure can be 0, volume can be 0, and in this scale, the Kelvin scale, the temperature can also be 0. So this proportionality is what we find in the laboratory. At one point, they thought all motion stopped when the temperature became absolute 0. Now we know that from quantum mechanics, there's some minimal motion that has the lowest energy state. Then we have Gay-Lussac. Gay-Lussac, or Gay-Lussac's law. Here the volume is taken to be constant, and And then we have the pressure is proportional to the temperature, which we can write here as P over T is equal to a constant, and to remind ourselves that the volume's constant, put a little V down there. Now we go to Gay-Lussac. Here what we do is we keep the volume fixed. Now if we heat up the gas, then the pressure will go up. So to keep that lid on, I need a greater weight to set that weight on that lid so that I can balance the pressure or balance the force of that lid. So just imagine here the pressure getting greater and greater because of the temperature. The molecules are going crazy. The gas particles are bouncing around like crazy. And then we have to have more force to hold that lid on to balance the greater pressure inside. So this is nice. We have each of these three, volume, temperature, and pressure, being held constant, and then seeing how the other two relate. Now we can combine all these into one equation. Look at the pressures in the numerator, the pressures in the numerator, the volumes in the numerator, the volumes in the numerator, and looking at all the cases. And the temperature appears in the denominator in both cases, that it appears. So we can write the pressure times the volume, the numerator variables, divided by T, the denominator one, and state that that is equal to a constant. Now when I write constant, doesn't mean it's a specific constant, just means constant in general, just a constant. Now I would like to look at one more law, and that's Avogadro's law. And for Avogadro's law, you have the same number of particles for all gases at a specific pressure, volume, and temperature. So that means that the constant is proportional to the number of particles. So that would be K times N. It's a lowercase k there. And when I write Kelvin, that is going to be an uppercase K. That's the abbreviation for Kelvin up here. I like to think of Avogadro's law as taking two containers of gas with the same volume V and the same number of moles or the same number of particles. We'll talk about moles shortly. Same temperature and same pressure. And if we bring these together, we can then remove the wall and we'll have double the volume, double the number of particles, and the pressure and temperature stays the same throughout. So here you can think of Avogadro's law as, with the pressure and temperature being a constant, that the volume is proportional to the number of particles. So you double the number of particles, you double the volume. So we can write the ideal gas equation as the pressure times the volume is equal to N KT. That formula there. Now chemists like to use moles instead of number of particles. And historically, moles were defined using a chemical element. For example, one case was to use carbon 12. Carbon, let's just take a second here to review some history. So the carbon atom has 12 protons and neutrons combined. And sometimes you can write this like this, although the 6 is understood. You have to have 6 protons. So In other words, you have 6 protons, and in the most common form of carbon, you have 6 neutrons, and this would be in the nucleus of the atom. In my other courses, I put the 12 and the 6 on the left-hand side, since that's the modern notation. I wasn't thinking because I was taught many, many years ago from books from the middle of the 20th century, and they would put it on the right-hand side. But the common notation today is to move those to the left-hand side. So what they did is they said, suppose we had 12 grams of carbon. Well, that's going to be a lot of atoms, and they call that then Avogadro's number. So Avogadro's number, if we look at the number of atoms in 12 grams of carbon, would be 6.022, and some more digits there, times 10 to the 23rd. Now in 2019, they decided to make Avogadro's number with an exact definition. So the number that we use today, if you want the exact number, is actually 0.022 and then a 140, put a little space in between, make it easier to see, times 10 to the 23rd. So this is exactly the case. That's Avogadro's number. And if you have that many of entities, you have, by definition, a mole. So here, we also have the Avogadro's constant. Now, when you have the constant, it's equal to 6.022. Now, I won't write all these out. Times 10 to the 23 entities per mole. So when you actually write the constant out, it has a unit. But if you wanted the number itself, it would just be this. That would be the number. It has no units. So there's a difference here we wanted to point out. So the constant is the Avogadro's number per mole. So to find the number of moles, we like to use little n. You just take the total number of particles, say n, and divide by the 6.022 times 10 to the 23rd, and that will give you the number of moles. So if we do that, then the ideal gas law, PV, is we replace the number of particles by number of moles, and we'll have a different constant, say called K prime times T. Now, if you are a chemist, this K prime is designated by R, the ideal gas constant R, which is often taught very early, like in chemistry, high school chemistry. But since the R in meteorology is reserved for something else, meteorologists will call it R asterisk. So this would be chemistry, and this would be atmospheric science. The atmospheric scientist wants to reserve R for something else, which we'll see in a second. So this gives us pressure times the volume, PV, is N R, the asterisk T, since our course is for meteorologists. This whole course is aimed at deriving lapse rate formulas. So we're going to call this equation 1. We're going to derive many, many equations here that we're going to be needing for our derivation of the lapse rate formula. Now, meteorologists deal with the atmosphere, and there's no fixed volume like a container in a lab. So we would like to use the volume per mass, or say the mass M of the air. So this is called an intensive variable because it doesn't depend on how much you have, because you have more gas, you have more volume, and it'll divide out. So if we look at that, we have, say, from the point of view of a physicist, might use a little v for that, but the atmospheric scientists, ATMS here, prefers to use alpha because they want to reserve v for something else. V is for vapor, and vapor is very precious in atmospheric science. So this is the definition for ATMS. So now what we can do is we can look at dividing this by the mass, say the mass that's in that volume, and this will be N over M R asterisk or R star T. Now what we would like to do is have the mass, big M, be the mass per mole. So that's going to be the mass that we have, and we're going to divide that by the number of moles. So this is the mass per mole. And that's also called the molar mass. Now let's look at the periodic table for carbon. I have these little squares here. So symbol C, the 6 stands for the number of protons in the nucleus, and that's what defines carbon. And then here you find another number, 12.0, say 107. And we said that carbon, typical carbon, has 6 protons and 6 neutrons. And since proton and neutron have basically the same mass, you would just see a 12 up there, but you have the 0.0107 because there are 2 types of carbon atoms. One is carbon 12, and then one is carbon 14 that we find, and these are called isotopes. Same number of protons, same number of protons, which would be 6, but here you have 2 extra neutrons. You have 8 neutrons instead of 6. So in the old days, when they defined the mole as the 12 grams, if you had 12 grams of carbon, you would have Avogadro's number. So you would have 1 mole. So that relates to the history a little bit. But going back to this general formula, you have the mass of your gas, and you divide by the number of moles, and that's the molar mass. So the chemical chart is convenient because for carbon, it would be basically 12 grams. In other words, 1 mole of carbon would have that mass. Okay, so if we proceed here with our formula, what I would like to do is go back to this formula here where I divide it by the M, and that would be the pressure times alpha, since alpha is V, big V over M, is equal to, and then here what I'm going to do is I'm going to write the R star and have it divided by, and flip this, M over N. So when you divide by M over N, you would get N over N times the R star. And since the M over N is the big M, we can write this as R star over the big M times the temperature. So let's look at a couple more formulas here. If we look at this formula, we're going to do what the atmospheric scientist does. They consider this as the gas constant for that particular substance. So this is gas constant. And it depends on what we're looking at. So in other words, we can write down pressure times the specific volume is equal to the gas constant times T. Now when we do that, we're going to call that equation 2, because we're going to have a few dozen equations that are going to be needed for our derivation in this course. So that's equation 2. And to emphasize the definition of R, a gas constant, we'll make 3 R star over M. And just to emphasize, this is convention in atmospheric science to do this. So the ideal gas constant in chemistry is that R star. And now for the fourth equation, what I would like to do is consider the ideal gas constant for dry air. So that would be R star over the molar mass for dry air. Sometimes this is called in this case, the atomic weight. The atomic weight is like when you do the average. So technically this would be the atomic weight because we did some average over the two isotopes, took that into consideration, the relative abundance. And then if you have the dry air, you would use a molecular weight for the molecule. So that would be 4. And then for equation 5, we'll have vapor. The gas constant for vapor would be R star over the molecular mass of vapor. Then for equation 6, which appears often in meteorology, is epsilon, which we define as the ratio of the dry air gas constant to the vapor gas constant. But now we have another formula, since if we look at this 3, we can write this one, epsilon here, as for the RD, you would have R asterisk divided by MD. And then here for the RV, you would have the asterisk divided by the MV. The R stars would cancel and this would flip up. You'd have MV over MD. So what I would like to do is for epsilon with equation 6, also note that this is MV over MD for equation 6. So now let's briefly discuss variables. If we look at variables, the pressure, the volume, and the temperature, or the specific volume, which is alpha, if you'd like. These are variables here that refer to the macroscopic gas. In other words, you have a gas in a lab, you're going to have, let's focus on these 3 here. The pressure in the lab can be measured, the volume can be measured, and the temperature can be measured. And these are called state variables, since they describe the state of the gas, and they can be measured in the lab. They're also called macroscopic variables, since they can be measured in the lab, and they're properties of a gas that's large, in contrast to, say, molecules and specific things like that. So to compare with a microscopic variable, you would have, for example, the individual masses of the particles and velocities of the particles. But for the gas in a volume in a lab, we can describe the whole thing with the pressure, with the volume, and the temperature. Now notice that the volume is not an intrinsic variable. You have to divide by the mass of the gas. And then you would have the intrinsic variables that here don't depend on how much gas you're looking at, since if you look at more gas, you'll have more volume. So these are some definitions that we encounter in our course, but more important, I want to look at the state variable. If you have a state variable, then if we were to look at a small change in the volume, we would have dV. And if we were to do an integral from volume 1 to volume 2, say it's expanding, the gas is expanding, dV, we would integrate this, we would have the volume 1 to volume 2, and that would be volume 2 minus volume 1. In other words, the change in the volume as it's after it expanded would be the difference of the final volume, this would be the final volume, say, minus the initial volume. And you might say, well, this is obvious. Well, it is for the volume, but we're going to see in our course that there are things that don't work this way. And one's going to be when we transfer heat and when we do work, when we get to that point. So this is called an exact differential when you can do this and have a dV that makes sense. That's an exact differential. And when you go from one volume to another, and it doesn't matter like how you do it, that's called path independence. You might say volume 1 went to some other volume, then that was there for a while, and then it went to the volume 2. So it doesn't matter how you go, or you can go directly to volume 2. Or you can go quickly to volume 2, or you can go slowly to volume 2. It doesn't matter. And then we'll see in our course, we have things like heat and work that are inexact differentials, and they're going to be path dependent. So this is a little preview of things to come, so some definitions. So that includes our chapter B on the ideal gas.